Thank you so much for joining us. I'm your session host, Jamika Marshall, and I am the Shadow the Scientist Programs Manager. Welcome to the 26A Gemini Users Session. Now, the Shadow the Scientist initiative is brought to you by an incredible team at the University of California, Santa Cruz, and funded through a generous grant from the Heising Simons Foundation. Now, the International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located, as you know, onto the best observing sites on the planet. Now, the North Telescope, I'm here actually in the Gemini North Hilo Base Facility right now, and the Gemini North Telescope is located, of course, on Maunakea as part of an international community of observatories that take advantage of the superb atmospheric conditions on this long dormant volcano. The Gemini South telescope, which we will be observing, we'll be shadowing the operator and observers there. You'll meet them in just a few minutes. This incredible telescope is located on Cerro Pachón in the Chilean Andes. Of course, make this another prime location for a telescope. Now, by incorporating technologies such as the laser guide star adaptive optics and multi-object spectroscopy, astronomers, you and the Gemini partnership, explore the universe in unprecedented depth and detail. And I would just like to say that this session is, of course, being recorded, and it will be posted on the Shadow the Scientist YouTube channel. Now, without further ado, I'd like to welcome one of our three science hosts, Brian Lameau, who I'm going to welcome now. We also have Si Su and Eric Steinbring. And in Gemini South, we will be shadowing Pierre King, who is the telescope operator this evening, and Daniel May, who is in the observer's chair. Brian, welcome.
Thank you so much, Jamika, for getting us started.
Absolutely.
So I'm Brian. I'm a staff scientist here at Gemini North. So this is really an international endeavor that we have right now. So myself, Sylvia here is a postdoc.
Hello, Sylvia.
Hi. Hello.
Jamika, we're all in Hilo. So not on Mauna Kea, but in Hilo, the Gemini North Base Facility. So we're adjacent to where we control the telescope here. We have Eric Steinbring joining us from Canada. We have Si Shu joining us from Arizona. And we have Daniel and Pierre joining us from La Serena, which is where they are operating Gemini South.
Woo!
Good, okay. So this is the new users session for 26A. As I mentioned in my email, we have like no real set agenda. So please feel free to introduce yourself on the chat. Please feel free to raise your hand and ask a question at any point. Please feel free to show your video. More than welcome. It's nicer to talk to faces, even if they're virtual. And we're gonna start with like just a little overview of Gemini Observatory in general, some of the science capabilities, a lot of which you probably already know, the kind of observatory ecosystem, which is important for you to know as a PI to understand how best to leverage the resources that we have here at the observatory. So maybe we can first just like quickly introduce ourselves, and then we could go to C for kind of getting us oriented. So maybe C, do you want to start?
Yeah, sure. Hello. Good afternoon. Good evening, everybody. My name is Si Xu. I'm an astronomer at Gemini Observatory, Nuala. I have a little companion here, my daughter May, who you might see in and out. Anyway, so I used to be in science operations, work closely with Brian in Hilo. But then I recently moved to Tucson. Now I work in the Office of Chief Scientist. I mostly do user support and user engagement. Very glad to have you here. Yes, so if you have any questions, please feel free to speak up or type in the chat.
And Eric, do you want to go next? Thanks, C.
Thanks. Thanks, Brian. Hi, I'm Eric Steinbring. I'm the head of the Canadian Gemini office. I'm just an astronomer, though. I'm a support astronomer, and I do all the jobs that the other support astronomers do in the Canadian Gemini office. I'll talk later about how NGOs work and help you get your data. But that's my role as a support astronomer.
Thanks, Eric. Daniel, Pierre, you guys want to introduce yourselves?
Yeah, sure. I'm Daniel Mai, and me and Pierre, we are science operations specialists, which is a role in the observatory in our lab that are more linked to the night shift, and also checking data during the day and being enrolled in observatory projects to make observations more optimized, let's say. So we are also astronomers, and we are here tonight to listen on your questions. And as you will know in a minute, we are close due to weather right now, so we have to take this as a good news to talk a lot and make a lot of questions and have this opportunity tonight. And so Pierre will present herself now. Yeah.
Okay.
My name is Tiera Kin. I am also a science operation specialist. In this night, I'm in the position of the operator. Is a person in general move the telescope, but now we are close. We don't have really a bad weather. Even it's a very beautiful night in this moment, but we have some condition that in this moment is not a good opportunity to open the telescope for a set. So, and now also we have this is in here, Reyes Cartis, and I don't know the students.
Camila Cárdenas and Guillermo Busquets. Good enough.
Hi, guys. Okay, well, thank you so much, and welcome everybody. Yeah, so I just shared now our status page for Gemini South. This is a publicly available page, and this is one that you should get to know really well as a PI. We have the Gemini North equivalent. This is all the conditions right now. So there's tons of monitoring information here. Recently, the Gemini South staff, in conjunction with some of the staff up here, added their cloud cameras. So you can see all the cloud cameras. I think this was just like 2 weeks ago that this was added. We've had this capability in the North for a while, but so this is, I think it's a loop of the last 10 or 15 minutes, the cloud cameras. So you can see it's a beautiful night there. Unfortunately, the dew point's a little bit high, so they're going to wait. They're just going to wait for this cooling trend to continue, which means if the last 2 nights is any indication, another one Shadow the Scientist session.
So just an hour, maybe.
Yeah, hour and a half, yeah. Lots of thermal inertia. Yeah, can I pass it over to you, C, to get us oriented? I'll stop sharing.
Yeah, sure. Thank you, Brian. All right, let's get started. Let me share my screen. And can people see my slides?
Yes.
Oh, okay, great. Okay, yeah. So, yeah, hello everyone. As I said, yeah, so this is a special Gemini new user session. So very great to have you. So it's basically maybe a 3-part thing. First, we will hear a very brief presentation about Gemini capabilities. And then we will do some phase 2 demo, if Malidoan will let me. And then we will also actually go into Shadow the Scientist and hear a bit more about how science operations go. At any point, if you have questions, please feel free to raise your hand or put it in the chat. And Jamaica O'Brien, please feel free to stop me if I didn't see the questions. Yeah.
I'm good.
Gotcha.
Also in the room, feel free to ask any questions.
Yes. Yes.
Yeah.
Yes.
All right. And we already said this is a very brief outline of the session. Yeah, we we just prepared a couple of slides, so we'll just go around. Yeah, and the session will also be recorded and shared on YouTube. Right. So all right, so let's start. Yeah, okay. Wow, like there's a sound, but I think it's Gemini South control room. All right, okay. Yeah, okay, you are all Gemini users, so maybe you don't need this, but this is a very quick overview of Gemini. So we have two 8.1-meter telescope in both Hawaii and Chile. And then we are optical and infrared capability. We do both imaging and spectroscopy. Gemini is have several international partners and include the US, Canada, Chile, Brazil, Argentina, Korea, and also University of Hawaii. And the Gemini is also part of the NSF NOAA lab. So it's in this bigger like US ecosystem. And here are two photos, one of Gemini North, one of Gemini South. I always ask people, can you figure out which one is North and which one is South? Yeah, you know, in the first they like look very similar. And I'm like, oh, I think I see the Magellanic Cloud. So that's how you tell why one is North, one is South. And they look very identical, but not exactly the same. Cool. And cool. Okay. Yes, Ghost. I will be doing some Ghost demo to set up phase 2 actually. Yeah. All right. And then here is an overview of Gemini capabilities. So as I said, we are really focusing on optical and near-infrared. We have both imaging and the spectroscopy capabilities. And then we also have some AO options at Gemini North. I will go into the details in a little bit, but if you want to read out more, I really highly recommend this Gemini capabilities brochure. This is the URL and this is the QR code if you want to go and take a closer look at it. Yeah, so just to move on. So first is at Gemini North. We break down into optical, infrared, and the AO capability. So in the optical, GMOS NOS is really our workhorse instrument. It does both imaging and long slit, IFU, MOS, so it kind of does everything. And then we also have Alopeke, which technically is a visiting instrument, but it's always there on the telescope as long as the support team is ready. The instrument and it can be used. It's a speckle and a rapid wide field imager. And also there's the Maroon X, which is actually also a visiting instrument. So this is actually a visiting instrument, but we are thinking about maybe make it a facility instrument soon because it's so popular. It's a red sensitive high resolution spectrograph. It's specifically designed to do radial velocity studies and to follow up an exoplanet, basically. And then in the infrared, we have two spectrographs, GNRS and IGRANS 2. But actually, you will see a little bit for GNRS, it actually also does imaging. It has some imaging capability, but it's mostly for long slit or cross dispersed spectroscopy. And recently, it have two new IFUs. And IGRANS 2 is our newest addition to Gemini North. It is a high resolution near infrared spectrograph. Which covers basically H and K band simultaneously. So it's contributed from Cassie. And then we also have this AO option with Altair, and it can be combined using with GNRS. So it's kind of a lot of information, but I just quickly gloss through. I wonder if there are any questions about Gemini North before we move on. Cool, I guess we are all good. I guess if you get the program, you probably know which instrument you want to use, right? But still, in case you want to start,
there are other instruments besides your instrument that you proposed for. So. We're very adept at switching instruments, turns out. So we actually do have a lot of programs that use like combinations of GNRS and GMOS or F2 and GMOS. I know there was a program recently that there was like a GMOS imaging followed by F2 followed by GMOS imaging in the south, and we were just doing a rapid TOO follow-up where we did we did GMOS and 2 gratings and then followed by GNRS, so you can get all the way from like atmospheric cutoff to 2.2 micron spectroscopy in the course of like 45 minutes. Not a bad deal.
Yeah, great. Yeah, actually, in a little bit, when I do my phase 2 demo, I actually use both GMOS and Ghost. So yeah, I'll show a little bit. But yes, nice. You can because our Q mode, the flexibility, you can use 2 or even 3 instruments simultaneously, right? All right, we'll move on to
Plus we have 2
Gemini.
telescopes, right?
Exactly.
That's true.
Yes. Okay. So for Gemini South, also optical, we have GMOS South, which is basically the exact copy, not quite, but exact copy of GMOS North. It also does imaging, long slit, integral field, and a multi-object spectrograph. And then we also have GHOST, which is our new high-resolution spectrograph, which I will show the demo in a little bit. And then there's also Zorro, which is basically the same copy and at Alopeke, but for Gemini South. So it's a speckle and a rapid wide field imager. And then, yes. And then there's also in the infrared, there's Flamingos too, which it does both imaging, long slit, and a multi-object spectrograph, but in the infrared. Yeah, so that's the main thing for Gemini South. Yeah. Okay, any questions? Oh, actually, maybe before questions, I like this. This is a more visual presentation about the Gemini capabilities in both imaging on the imaging on the left-hand side and the spectroscopy on the right-hand side. So imaging, it kind of show you the field of view, right, of GMOS and the Flamingos too. And then Alopeke and Zorro is there's narrow field and wide field. And then also geners in this purple. So that's why geners have this limited imaging capability. And then in terms of spectroscopy, here we are plotting in terms of wavelength coverage and also resolving power. So yeah, I think this is kind of a nice visualization, depending on your exact kind of science. All right. With that, I will also say, because Gemini have several partners, so we also have National Gemini Office, which helps support this effort. And then, excuse me, today, very lucky. Yes, I'm doing okay here. Okay, I think I'll hand on to Eric. So please go ahead.
Thanks.
Take a sip of water, see.
Take a break.
Yeah, sorry.
Hope you're okay, Steve. Yeah.
I forgot to say these sessions are strenuous, so yeah, you had to hydrate beforehand.
This is true. This is true.
All right. Well, you look like you're okay. Okay, thank you. So I'll speak on behalf of the National Gemini offices. I'm with the Canadian Gemini office, and each partner has their own office, which is typically small. It's typically 2 to 6 people within each partner organization. We're your access, of course, to other facilities within each of those partners as well, apart from Gemini, right? So in effect, these are national observatory offices. NORLAB in Tucson, Canada's in Victoria. Here I'm in Victoria. I'm at home, but the observatory is just up the hill here. And Brazil, Argentina, Korea, and also Chile and Hawaii have their own offices too. You should see these folks as your first contact in connection with partner time on the telescopes. These are the folks who are responding and organizing the semester calls. Call for proposals, which have slight differences between partners. We're not directly perhaps connected to we're not directly connected to the LLP, the fast turnaround, or the DDT time, but for the regular semester calls we are, and we coordinate through an international time allocation committee as a representative for getting programs, your program that you got on this semester, getting that on the telescope and into the queue. So, and placing your program in the queue via the ranking that was by the national tax. So we help with that process. We don't hold the time ourselves, but we answer to our board representatives, and the national organizations that do hold the time. So we are your advocates. Typically, we do phase 1 technical assessments for proposals. We're not blinded to phase 1 proposals. Can't be, because we need to know who's submitted, and we relay those to our TAC representatives. We are all astronomers, and the nature of these positions are typically that they vary among the partners, but we're typically seasoned astronomers and have experience with different telescopes beyond Gemini, and what resources you have otherwise as well. So we're a good contact that way. But we're working for you. those as TAC peers, so as people who are senior folks and possibly on tax, when each community we assess and rank proposals prior to the ITAC process, but we coordinate with that process. And speaking for Canada, and it's useful for you to know and communicate with your NGO partners about the rules for proposals, which can be slightly different, and the in-house expertise. For example, in Canada, I mean, our date will be different for the submission of a proposal than the US or the other partners. And there's won't be language difference if you don't submit in French, but that might not be true for the other partners. So it's just, there are differences between them. We advertise and coordinate within our communities too. So we're your de facto representatives on, for example, in Canada, it would be CASCA. We want to hear from you. We organize email reminders, sessions at annual general meetings, for example, the AAS or CASCA. There's phase 1 writing workshops. I know Korea runs workshops for writing proposals. We are your contact and advocates for long-term planning, so the decadal survey in the US, the long-range plan in Canada, and others. Like there's overlap between the National Gemini Office and your STAC, your Science and Technology Advisory Committee members that serve on the Gemini Advisory Board and the Users Committee. We can get you in touch with those people. We may be one of those people on that committee, for example, depending on the office. Within the Ops Working Group, which is a group of the offices that helps deal with the operation of the telescopes, and your board members. It's very safe to say for all, on behalf of all NGOs, please talk to us. Please contact us. We want to talk to you about your experience with the observatory and what would be, how to help, how to make it better. That's our job. For almost all cases, we are your phase 2 primary contact. As some people I see here from Canada, some of you may be among my phase 2 contacts. We have 4 members here. It's different for each partner, but pretty similar. And we can cover all modes of all instruments, unless it's Subaru or a special visitor instrument. Sometimes we don't take care of those. Because we have ability that's sufficient to get your program, your phase 2 set for activation. In some cases, there's more than that. Sometimes there's expertise in one NGO that isn't in another, and that's shared amongst the NGOs. And also lately, also for fast turnaround programs as well. And because so many programs are in this partnership are joint. We also can get in touch across the partner offices as well. So I think to kind of summarize, we remind, help, and are otherwise generally available to you, including with contact within Gemini, for example, to contact Gemini. We're primary contacts for help desk tickets. For sure, things like phase 1, when you're getting ready to propose, we're good people to contact and ask about details about differences between the proposal processes. And we do technical assessment. Almost all the partners do technical assessments of all proposals. We are probably the people that are doing the technical assessments and can talk about can help with that. And if we don't know the answer, we know who to get in touch with. So we know who to contact within Gemini, for example. Our primary goal, of course, is good scientific results from the partner share. So that's our metric. So also look to us and directly to Gemini and Noir Lab outreach PR folks for press release contacts. For example, in Canada, that can be within National Research Council, or it can be with Noir Lab NSF for things like press releases, media things. We answer to the organization that holds the time or and those are those people. And when you look good, we look good. So we're looking to advertise your results. We are looking to see that theses are completed. We'd like to see high impact implications, high impact publications, and we relay those metrics, those information to our funding agencies. So your office, your National Gemini office is a good way of showing how you shine. That helps us too, but that helps everybody, right? So that's meant more broadly, and maybe just to kind of finish. I hope I convinced you that we're good people to talk to. The contact information is like your local office. The information is on the Gemini front page. You already see it, of course, when you applied for your time. That contact information is the way to get started if you're have to ask a question. But for other things too, beyond press releases and things. For example, if you're interested in Gemini, interested in instrumentation, for example, in Canada, relay to those instrument groups. For example, something was mentioned of GHOST. Well, GHOST was in part built here at NRC, and we know the people that built it, so we can get you in touch. So that's another way that the Gemini offices are useful, and getting you in touch with other aspects of the observatory. Its technical aspects as well as science. Thanks.
Thank you very much, Eric. That was a wonderful overview of at least part of the observatory ecosystem. And yeah, I want to echo a lot of what the sentiments that Eric shared, which is that this is really a team game. And we're all scientists. We all work really hard to facilitate science, our own science and student science, postdoc science, and our user community science. I observe on a lot of telescopes, including both Geminis now. And so I know fairly well what it takes to be successful on these telescopes, and the deep technical aspects of at least the instruments that I help to support. But I also have lots of gaps in my knowledge, and this is where other team members are able to pick that up. So, for example, Daniel and Piera know Gemini South much better than I do. They spend a lot of time on night shift. I don't as much, and so they have a deep knowledge of the nighttime operations. But we work. Communication is really, really important. Communication with for the NGOs, with funding agencies, and then down to the users, our communication with the NGO and to the users. So actually, we're usually the secondary support for a lot of the programs. So you'll see usually an @noirlab.edu secondary contact scientist in your program. So that'll be a staff scientist usually. And also Sylvia is now taking over some phase 2, just having arrived here. So right into the fire. And so I work with Eric quite often. So he'll do the initial assessment, the technical assessment, and then we'll kind of iterate around, and then get a final assessment for maybe some of the peculiarities for maybe I'm more up to date on one instrument because I did something this afternoon with the instrument, and so I know more than what Eric knows. And so I say, oh, hey, by the way, there's this noise in this quadrant, and we should shift and move this thing. So we all work together hand in hand, but it really comes to Q observing is a weird kind of way of observing. It's not something that I'm used to. I've now been here for almost 5 years, and I'm starting to get used to it. But it takes a lot of communication, both vertically and horizontally, to get it right. And we have tons of roles here at the observatory. We have people that work on night operations. We have people that do contact scientist work. We have people that coordinate the queue, the people that do that coordinate all the science operations, both here at the North and the South. And we all take on these roles at different times. And so we have ability to understand the perspective of each one of these roles. And so just overarching message is reach out, use your resources. I'll talk about some of those in more detail in a second. But there's mailing list for all of the instruments. So if you're using GNears, which is, I'm an instrument scientist for GNears, there's GNears_science at gemini.edu. You email that email address, and you get probably 13 staff scientists that get that email. And we're really willing to help. It helps us a lot if we have communication at the front end. This is why we do the phase 2. We make sure that everything is set. So once the second that Piera and Daniel are able to open, dew point drops low enough, they're able to open, we can use every precious second of that time for the science and not for any random phase 2 issues. So that's our goal here. Okay, so let me go on in the formal talk. So, okay, so there's lots of different ways to interact with the observatory, just in terms of getting science time. The one that you're all certainly familiar with at this point is the normal Q observing mode. So this is the normal semester boundaries. So we're right at the end of 25B here, and then we're entering into 26A in a couple of weeks. And most of the programs that we let's say host at Gemini are normal Q mode observations. So they're ranked into 4 different bands. Probably you already know this. 1, 2, and 3 are the kind of normal Q modes. So band 1 is the one that takes the highest priority at night, but that priority system is very, very complicated. And so it's not always the case that a band 1 beats a band 2. Timing windows matter, right ascension matters, conditions matter, so on and so forth. So actually, there's plenty of times where a band 2 or band 3 program will finish off faster than a band 1 program of equal time. And it may be because the band 2 and band 3 are a bit more flexible, or that the instrument modes that they can use are more. So there's a lot of ways. One of the things that I'd like to impart in this session is there's a lot of ways to maximize the observability of your program, and to even if you're, don't give up if you're a band 3 PI. We've actually completed most of the band 3 programs this semester. And it has a lot to do with flexibility of the program, and that has a lot to do with communication with your NGO contact scientists, and then with your NOR lab contact scientists. Band 4 is a special category that you can apply to at any time. That's a poor weather variant. So basically, one of the constraints has to be very bad. So that could be terrible seeing. That could be a couple magnitudes of extinction with clouds. It doesn't mean that your observation is going to be taken under those conditions. It just means that your program can accept those conditions if those conditions show up. But if we're open, we want to be using that time wisely, even if there's tons of clouds. And so these types of programs can be submitted to our head of science operations at any time. And if they like the idea, then it can go forward, and we can make a regular kind of normal Q program out of that. We have plenty of programs that are latent target of opportunity programs. So they basically sit around waiting for a trigger. So it's very normal. About, I would say, 10% or so of our programs are just programs that are waiting for something to go bump in the night, and then they trigger. And there's 2 different flavors: rapid target of opportunity, which is best effort we try to get on in 24 hours. And actually, like for the 3i Atlas observations, these latent programs were sitting in both observatories, so that no matter where something shows up in the sky, we're ready for it. And so it was actually triggered on both Geminis roughly at the same time. And then there's standard targets of opportunity, which is we try to get best effort in 72 hours. But people can always put custom timing windows in there. There's a priority visitor mode. So if you are a band 1 PI and you'd like to come visit, we would welcome you here. And we would welcome you by allowing, after a little bit of training, allowing you to use our telescopes. So you can actually take over the queue, and you can execute your program on that night that you're observing. If the conditions aren't good enough, then you would act as our regular Q observer. So we would train you. You'd probably be sitting with a staff scientist. So it's a nice incentive to get a Band 1 program. You can actually you get the benefit of Q, where you get to kind of sit there the whole semester waiting for really nice conditions. But if you want to just, I don't know, jump the line, you can do that as well. So it's a pretty cool feature. It's not utilized nearly enough here at the observatory. So please come visit us. Well, please get a Band 1 program.
Step 1, Band 1 program.
Band 1 program, then come visit us, or just come visit us. It's nice.
Yeah.
You can watch night operations, but you can take over the telescope if you have a Band 1 program. So that's really neat. We also had a graduate student visitor program. This was a really neat program where we had graduate students that were PIs, and they came to visit either Gemini South or Gemini North. It's on hiatus right now, but we're hoping to get some seed funding for that to eventually bring that back. And so I think we had six visitors or something, 3 in the South and 3 in the North. Was it a little over a year ago? And yeah, that was very exciting. And they got on the job training. They got to do night operations, all this kind of stuff. So that was really fun. And then there's classical mode. So this is not used very often, but this is you were assigned a night, and you get that night, and you have your targets set up ahead of time. And it's actually kind of the worst of both worlds, because in what I'm used to, classical nights, you're kind of given the keys to the telescope, and you're able to observe what you want, at least within the framework of that particular instrument. Here, you actually have to set up your targets ahead of time, and you cannot change them. So you have to kind of set up any possible target that you would want ahead of time, and then you're given that night, and you get the conditions that you get, and then that's it. So it could be that there's spectacular conditions and you luck out, or it could be that we're sitting with high humidity all night and But we had a graduate student led classical program last semester. Kilauea went off, so the volcano here went off, and SO2 off gassing combined with decently high humidity, not good for telescope optics. So they sat there all night waiting for the particulate counts to go down. It didn't, but we actually converted that program into a Band 4, and the PI got all of their data. So we're flexible as an observatory. So we do have kind of safety nets there sometimes. So we have fast turnaround mode. This is a really cool mode. So this is one that a lot of staff here support. And I know Eric mentioned it briefly. So the NGOs are starting to get involved as well in this program at the level of doing checks. It happens really fast. So it's a call every month. The proposals come in. We do a quick assessment. There's a technical assessment. It's a distributed peer review. And that process is all done within 15 days after the proposal deadline. The proposals are ranked, and by the 22nd of every month, we send out announcement emails. And if your contact scientist is on it and you're on it, within a couple of days, you can get everything set up. And we've had programs where people have submitted a proposal and then got their data within effectively 3 weeks. So that's not a mode that's available to any other observatory that I know about. Is beyond through a DD channel. So this is a codified process. It's a quick process in the sense that not only the timescale is quick, but the science justification is 1 page, and then you have I think a page for figures. So it's just, you have an idea. It maybe doesn't take that much telescope time, under, let's say, 4 to 8 hours. So part of a night, and you this is a good idea, or it's I need to finish off some targets from a program that I have before, or I want to synergize with some observations that I just took on Keck or with James Webb or whatever. So, and then you just put this in. It doesn't have to be you need these observations now, so there doesn't have to be a fierce urgency of the moment kind of thing. But just that it's a convincing use of telescope time in kind of a 4 to 8 hour chunk. And it can even be I've seen proposals for half an hour for an hour. So it could just be a little chunk of time that you need to finish off, some thesis observations or whatever. And it's a really good opportunity to see successful proposals. So it is a distributed peer review. There's not a lot of overhead associated with reading just one page of science justification, and you get to sample a lot of different types of science that's done at the observatory. So I think that helps scientific literacy for everybody in proposal writing. So it's been helpful for me also to read the proposals. There's DD time. That's another way that you can get time at Gemini. So if you find something really spectacular, please send a DD proposal, and this will be evaluated by a group of scientists here. And then it'll be evaluated on its merit. And if we give you the time, then it's usually a 1 to 2 day turnaround time, and then you're right on sky. And DD programs are the highest priority programs here. So they go right to the front of the line in the queue. So our metric here at the observatory is complete as many programs as possible. Our completion metric is actually 80%. So if we get to 80%, we more or less call that completed, though we very much like to get to 100%. And the main metric is completing band 1 programs. So that's where our priorities lie. And then as the band 1 programs get finished, then we move on to band 2 and band 3. But it's not as simple as that, as I mentioned earlier. So there's giant matrix. What you're seeing on the right here, this graphic, this is our queue planning tool. This is used by our queue coordinators. So these are staff scientists with the role of managing the queue every day and every night. We usually take week-long shifts for this because it's a super intense job and you're on call 24 hours a day, basically. And in the upper left part of this graphic shows, a list. And this list is a variety of different instrument capability, let's say, plans. So if we, like for the first 2 items there, it's LGS1 and LGS2. So if we have laser guide star capability active that night, then you would go to that plan. If we don't have laser guide star capability, or there's shuttering windows that don't allow us to propagate the laser, then we would go to a different plan. And so the queue coordinator during the day makes up somewhere around 10 to 15 different variants, all planned that contain all different queue programs that are appropriate for particular conditions. And then the observer, tonight Daniel at Gemini South, when they open, they would assess the conditions. They would say, okay, we have these like designations for weather. So we have like image quality, you guys all know from the proposals, IQ. So like IQ 70 is 70th percentile best seeing or better. And then we have like CC, cloud cover. So CC 50, both at Cerro Pachón and Maunakea, means photometric. So it's photometric about 50% of the time. CC 70 is like 0.1 magnitudes of extinction, and then it gets worse from there. And so Daniel would assess the conditions, and then he would go on to pick which variant that he would use for that moment in time. And then perhaps 10 minutes later, when the conditions change dramatically, then we would pivot over to a different plan. So one lesson that I'd like everybody to take, which I mentioned earlier, is be flexible on your program constraints. And this is something that I do with like every PI that I work with, is use the integration time calculator. There's one embedded in the OT. You can also go to the specific instrument on our webpage and use the ITC there. But check, you may think that you need like IQ 70, CC 50, water vapor 50, so on and so forth. But if you go into the ITC, you actually may want to make like a decision tree. So like for some of the programs that I've PI'd or that I support, I would say, okay, I can accept IQ 85 and CC 50, or IQ 70 and CC 70, or some variation there. And so you don't just stay rigidly at your constraints, but you allow a variety of different constraints to satisfy your program. And so it allows a lot more flexibility to creep in. and your observations to fall in places in the queue where it wouldn't if you just kept that rigidity. So you'd be amazed, like the difference between CC50 and CC70 and almost any observation is near negligible. So there's certainly cases where you want to make sure that you're at CC50, especially if you want to flux everything correctly. But if you don't, let's say you're just, I don't know, you're measuring a redshift or your relative line strengths or something like that, then you may not need CC50. So double check that and work with your NGO contact scientist to see if you can be more flexible. I'm going to pause. Are there any questions or anything, Eric? See,
I don't have any questions in the chat right now at all. But as I said earlier in the chat, if you have a question or a comment, you can raise your virtual hand and you can unmute yourself, of course, and make your comment or question, or you can address them in the chat.
Thanks, Jamika.
Absolutely.
I'll go a little bit faster because I think we got to do some phase 2 examples and stuff, get down to the nitty gritty. So yeah, there's a card game. This was made by staff about 10 years ago, I think. A little under 10 years. But it's actually like reasonably fun. And it gives you an idea of like how the queue system works. So unfortunately, it's a very limited quantity that's available at the moment. But at some AAS meetings, I don't know if we had them this year, but some AAS meeting, no, okay, not too bad. Eventually, we'll get them back. Yes, in your downtime as a graduate student or a postdoc, you can even still do science by playing this game that teaches you about the Gemini queue. But it's actually helpful to like understand how the queue works. It has like fealty to reality, and it's quite frustrating at times, just like the queue. Okay, so there's plenty of ways to get help, as Eric mentioned, I mentioned earlier, and CE mentioned. There's the websites, there's all the instrument teams off of the website, so you can email primary and secondary contact scientists, including the NGOs. There's the Gemini Help Desk, which Eric mentioned. So you can submit a ticket there and somebody will get back to you. And we have like a kind of escalation system. So I end up getting tickets of like really deep technical questions about gene years. So if it finds its way to me, it's trouble. And then we have a presence at every AAS meeting. CE was just there. There was plenty of like data reduction demos. The US NGO does a wonderful job of showing off the capabilities there. And then there's town halls and all sorts of special sessions and everything like that. So we're here to help. There's plenty of ways to help. As you all know, phase 2 deadline already happened. So if you don't have your phase 2 in, time to do it. If you are running behind or whatever, don't be bashful. Write your contact scientist. If you're like, the OT is like, the observing tool is not like the most intuitive system in the world at all. And so, I mean, it took me a long time to figure it out. And there's so many, it's really powerful, but there's so many like sub capabilities of instruments, and like, especially like an instrument like gene years where there's a huge number of capabilities in general. The OT has to be very flexible, but unfortunately that means you could click on the wrong thing, have no idea what just happened, and then just anyways, contact your contact scientist if you get confused. That's important. There's tutorial videos on the website. After this session, I'm going to make available some of the instrument scientists did sessions where we did like phase 2 demos to the NGOs, and we recorded some of those, and so I'll make that available in a follow-up email along with the recording of this session. So I know I did one on gene years phase 2, so I'll skip the gene years phase 2 today, but that'll be available in the video. And then there's this URL at the bottom here, QR code. This is a set of phase 2 reminders that we as instrument scientists actually sent to the NGOs about a year ago. And so these are like really down in the weeds details of like technical things of an instrument, but your instrument's on there. Whatever instrument you applied for, it's on there almost certainly. And so reading those can be helpful if you just get confused or you want to maximize the I mean, the settings in the OT matter, and if you want to maximize the signal noise of your observations, it's important to pay attention to those details. Yeah.
Do have a question. There's one of our participants would like to know a little bit more about the eavesdropping program.
Perfect. Yep, this is the next slide. Yeah.
I promise I did not see that slide before I asked that.
Yeah, so eavesdropping is available for band 1 and band 2 programs, if including FT. If you're band 3 and you'd really like to eavesdrop, please let us know and we can probably arrange for something. It's pretty simple. So there's on your announcement email, there should have been a link that goes to a Google Sheet where you can just put in your contact information. And you can just say when you're available, like let's say you don't want to be contacted on weekends in the middle of the night, so you don't sign up for weekends, but weekdays you're fine. So then you put your contact information there, and then you put a yellow note in your program that says the details of what you want, and then it gives a designation for the various contacts. And you can actually designate other people in your program too. So let's say you want your co-I to be contacted on Monday, Tuesday, Wednesday, and you're fine with Thursday, Friday, you can actually embed that into the sheet and then into your notes. So distributed workload. It's always a good thing. So it's very easy. And if you have any questions about it, just ask your friendly NGO or contact scientist. And so the idea is we call you about 10 to 15 minutes before a SLU. This is best effort. So if things are really hectic, sometimes we don't. But we'll try our best to do that. We SLU to your target, and then we share the observing screen. So just like I'll share some of the Gemini South screens a little bit later, it'll basically be the same thing. So you'll be looking at the active screen, and then you can ask questions as you want or follow along with the observations. And then as a reminder, your data is instantly available to download for most instruments. And then also, like for example, Ghost has the reduced data on the archive after it's finally reduced. Yeah, so there's tons of support even after the observations. The help desk is always there for you. Contact scientists, even if we're 2 semesters removed, feel free to write us and ask us questions. And if we can't deal with it, we'll find somebody that can. And there's a whole team of people here that work on data reduction. So the Dragons package or Gemini IRAF, these are data reduction packages that we offer to the community. And then we also reduce data for at least some of the instruments, and then make that data available on the archive. And of course, the help desk is there if any issues come up. And then I'll just mention that Pipeit is another software that a lot of people at the observatory use, including myself and others, to reduce Gemini data. It's an open source Python data package that is used for tons of different spectrographs around the world. So that's a useful tool. Even if you just want to compare like Pipeit data reduction to Dragon's data reduction, that can be very useful to see the subtleties of each. Yeah, and this is just a little thing about Shadow the Scientists. So I'll pass it back to maybe CE if you want to do like a phase 2 thing.
Yeah, sure. Do we want to do a phase 2 thing now, or do you want to see more with the control room right now? How's the condition? I guess the same.
Can we check in with Pierre? And they look too relaxed. Okay.
It actually looks like the dew point is raising. Daniel, you guys are still monitoring down there? Daniel, Pierre, can you guys hear us? It looks like they're demonstrating for the students.
Oh, I see. That's right.
Yeah, sure. Then I can go ahead.
Yeah, sounds good.
Okay, yeah. Oh, I guess maybe just one thing to add. Thank you, Brian, for the very detailed description about how Gemini works. One thing is we do have the Gemini program platform that's coming up that will replace our current PIT phase 1 and OT phase 2 tool. So we actually already did some an initial test with the GMOS, and in August, it worked pretty well. So soon, there will be more more opportunities for help us testing, and then eventually it will replace the whole thing. So as Brian says, right now it's just a little bit chunky, but the new tool actually works really well. So stay tuned, and I think we will have that soon. Yeah. Okay. So with that, then maybe I will do a demo. Any other questions? Any other thing before I move on?
No other questions in the chat right now, CE.
Okay, great. Yeah. Okay. All right. So I'll do a demo. Hopefully, yeah, everybody see my screen?
Yes, we see your screen.
Okay. All right. Sorry, I'm one of those PIs who have done anything for my 26A program. So anyway, so when, well, but see, I saved it for this event. Anyway, so when you log in, right? Oh, okay. Eric, are you gonna log off? I guess. Yeah.
Sorry, I have to sign off now. Thank
Okay.
you.
Thank you, Eric.
Thank you.
Bye-bye.
All right. I'll continue on. Yeah. Right. So I guess at the PI, when you log into your program, you will basically see something like this, right? So this is kind of your cover page. And here you have your program title. This is the investigator email. And see, so since it's me, I'm also my own principal support. And then there's another additional support. So it's actually a Gemini South program, and I am monitoring a very interesting white dwarf. And I want both GMOS and the Ghost, actually. So let's see. The first step when you open up is you see this template, right? So you can click on the template and say apply template. I think this is actually a very important thing because you don't want to be editing your template. So template is something you get from your phase one, like PIT. So before you make any edit, you really want to do apply template, okay? So now you see like it comes, right? To two. One is GMOS South imaging, and then another is Ghost. So this is exactly what I was talking about. I would like to do a GMOS South imaging to get the brightness of the target. And then afterwards, immediately with Ghost spectroscopy to take a spectrum of that system, okay? So we can go down to see, kind of open up, see how you do that. So for GMOS imaging, it's actually pretty straightforward. It's basically point and shoot, right? So you can open up this and open up this. So here are some basic setups for GMOS. Right, so what I personally like to do is you can click through different buttons. So this is a basic setup for GMOS. And then here are the observing conditions. So this is my required condition. So CC 70 and IQ 70. This is timing windows. We can worry about that in a little bit. And then so this is my target. And then so it's always useful kind of to double check the coordinate, proper motion, if everything was done properly. And then another really useful thing, if you click target and you see the image. Okay, let's see. Did it come through? Okay.
Yeah.
Yeah, okay. So it kind of give you an idea, right, about this overall field of view. And you see this automatic guider selection already help you select the guide star that work pretty well. So I'm like, okay, all right, I guess you don't need to worry about. But occasionally, if the automatic guider didn't quite work, you might need to change like the position angle and see if you can find a better guider. But usually the system kind of take care of that. So this is all green, so which means good, right? Yeah. And then one trick I really like a lot, and is actually the integration time calculator is actually built into the OT, which is super useful. So what I would like to do, since I'm looking at the point source, right? So I can just say here, I can say it's a point source. And then I can just use a black body. It's actually a very hot white dwarf. So I'm just going to use 50,000 Kelvin. Okay. I know it's a very hard one. And then when you click on sequence and when you do this ITC imaging, actually it already calculated for you with my current setup. You see like the signal to noise ratio is 300. So it's very high. I actually only need a signal to noise ratio about 50. So just want to say here, maybe another way to see it, if you click on sequence, you see I'm doing like U band imaging, I band imaging, Y band imaging, right? So I want to do 3-band imaging. And then this is exposure time. And then they do some slightly P and Q offset. just to dither a little bit. So with this ITC thing, you can see the signal noise ratio is actually very high. I don't really need such a high signal to noise ratio. And also when you click on this imaging part, you see this whole time take 30 minutes, while I'm hoping to maybe take about 20 minutes, right? So what you can do is you can just edit the time a little bit. Because U band right now is 160 and then it's 30, 30, right? So we can maybe do a little bit shorter, maybe 60 and then 20. Okay. You can see a little bit. Okay, now let's see what's the signal to noise ratio. Okay, I guess we can, you don't do it on the fly, but this is kind of the idea, right? Like you can actually get your signal to noise ratio and then you can see how much you need to change in order to meet your required signal to noise ratio. And I think that's kind of it for GMOS imaging. And you see when I
sorry, one other thing I'd like to point out. Can you go back to the sequencer, the top level?
Yeah.
Yeah, so another thing that's really important to pay attention to, which trips us up a lot actually, is the peak percentage full well. It's right next to the signal noise signal. This is where you can tell whether you're going into the saturation nonlinearity land. And so like if C were to bump up the exposure time to like, I don't know, the maximum GMOS exposure time is 1200 seconds because they're basically cosmic ray collectors. So that would put the peak signal probably 200 to 300 times the well depth. So you would like well saturate the CCD. And so for these observations, not that important because she's way below the saturation limit. But it does happen a lot, and especially like, yeah, there we go. G-nears is one. It's tough in the near infrared because like the CCDs for GMOS are basically linear all the way up to the saturation point, more or less. But G-nears is not like that. So there's definite like nonlinearity that creeps in. So the OT will warn you. You get these little warnings down at the bottom. But you know, things are hard. This is just a prediction. And especially in the near infrared, the sky background can modulate quite a bit. And so you want to be conservative here and usually stay below 50% well depth. And one of the other things that I'd like to point out, see if you maybe you can go back to your like just 60 seconds.
Oh, yeah. Fine. Yeah.
So you requested SBNE, CC70, IQ70, water vapor, any, those were your constraints. But we may not observe under those conditions. We're bound to observe at those conditions or better. Right. So if you were to like do CC50 and IQ20 and air mass 1, if you did like on the conditions right there on the like on the main thing there, you can just modulate the like conditions. If you just go to the sequence.
Okay. I was just going to do
I don't think it does populate there. Oh, okay. All right. I didn't realize that. Okay. And then you go to like air mass 1, for example. So this is a good thing to check always. So like the full well, the peak signal for the, what is that, I band? It jumped by like a factor of 2, right? And so we could easily be observing under these conditions. And so you want to make sure that your observations can handle also really good, you'd hate to waste like really awesome conditions. And so double checking that is important. Thanks, E.
Yeah, no problem. Yeah, I was gonna say, I think it matters a lot more in the infrared. Luckily, in the optical, it's not too bad. Like, but still, I think it's a good thing to double check because this target is still 16, almost 17 magnitude in V band, so it's not an issue. But quite often, like I feel like with the Maroon X, with the other instrument, if you're getting really bright, like fifth magnitude object, like sometimes that would really matter a lot. But yes, I think it will be good to. I actually didn't know you can change here. So good to know. Yeah. So this is another you can change.
We traded.
So, yeah. But the C here, if I change to CC50, IQ20, there's a problem, right? It will tell you, hey, I'm not allowed to use this condition because my actual program is requested in CC70, IQ70. So now I'm changing it back. Anyway.
Sorry. See, one thing I'll mention there is that if people are playing around with their ITC and they realize oh, actually, to do the science, I need a little bit better conditions than what I thought. Like, let's say C was playing with this and realized, oh, I actually do need CC50. You can email your contact scientist. They'll get you in touch with our head of science operations, and you can explain your case. And it is the case. We want you to get good science out. We'll check the queue and make sure that it can handle it. But there's a possibility that we can upgrade your conditions if you show that it's required scientifically.
Right. But on the
Better
other
to get
hand,
it right the first time. But
right. But on the other hand, if you decided you don't need such good condition, if you only need the CC IQ 85, you have no problem changing here. Okay. Like, that's definitely fine. Like if after you some play around, you're like, oh, okay, I actually only need IQ 85, then you can just do it without asking for any permission or stuff. That's fine. Yeah. It's only when you require better than your approved conditions, you need some additional approval. Yeah. Okay, so that's GMOS imaging. We'll assume it's done. I won't do it, but if it's done, you can set it for review, right? And then just want to make sure you click this sync button, because then that actually will trigger an email to your contact scientist saying like, oh, hey, this program is ready for review. And then the contact scientist will have the superpower to change it to the other conditions. Basically, you want it to be prepared because right now it's yellow, right? This color is yellow. And once it's prepared, it will be in green. That means they are ready to be executed. So for now, I'm just going to change it back since I'm not quite ready yet. I still need to play with my exposure time a little bit to make sure I reach the required one. But anyway, in the interest of time, I guess I will just move on to Ghost. But if you have any questions, please put in the chat and happy to answer. Yeah. So the second part of my science is actually ghost. So I decided to do GMOS imaging first is because then it help you kind of already in that, or maybe ghost doesn't matter. I mean, I was just thinking with GMOS and you're already in that general part of the sky, right? You're doing imaging. And then if you're pointing right there, then the ghost spectroscopy there will just be a little bit faster. Anyway, so if you open up Ghost, Ghost is actually a very simple instrument. It's just point and shoot. And you can see all the setup pretty much mirrors GMOS, right? It's like all the section is the same. And the only part is this Ghost part. And actually, the only thing you can choose is really the exposure time and the binning. So yeah. I guess it's also position angle. And then this resolution is actually what comes from your phase one. So you can do standard resolution or high resolution. The position radial velocity mode is not quite ready yet. And then right now I'm using standard resolution. So you have two fibers. So you can also do just single target, but typically since you have another fiber, you might as well just put it on sky, and then so you can get a target, both target and sky, right? So, and for my case, I just need 1800 seconds times 2, and 2 exposures. Yeah, so all this you can kind of set up in your ITC, and I want to need like 2 pi 2 binning. And then in general, the readout mode, it's strongly recommend not to change it because these are the relatively well characterized mode. So if you have a strong reason to change it, I think they still recommend you talk to the contact scientist, but otherwise, it's recommend not to change the readout mode. And I think that's pretty much it, actually. And then here's also the observing condition, target. You can kind of also go use this imaging, just take a look, make sure, oh, it find a good guide star, right? So everything's okay. Yeah, I think that's actually that's about the setup of the ghost.
Yes, it is. Oh, sorry. Hello. So we have a question. So just to double check, the Ghost ITC isn't integrated into the phase two OT yet, correct? Just want to make sure that they didn't miss it. This is from Solveig.
Yeah, I am not sure, but I guess it is observing wavelengths is not defined, missing filter. Yeah, so I guess not. I haven't quite used the Ghost ITC on this. Yeah, Brian, do you know this? Yeah.
No, I don't use Go.
Yeah. Okay.
Okay, we're getting an echo now. Yeah. Okay. Okay, that's better.
Yeah.
Okay. Yeah, I don't know. I don't use Ghost, so that's like the instrument at the observatory I know the least about. But yeah, that looks like an OT issue there. So that's definitely something I could bring up here to the relevant parties. But yeah, it doesn't look like it's working properly.
Yeah, it doesn't
You'll
seem
also
like.
notice this for Genius IFU. So if anybody's using the IFUs for Genius, this is a relatively new capability of Genius, like a couple of years. The ITC breaks. It just gives you like this nondescript red bar with a X. It doesn't even tell you, there's no text there. But in those cases, you can use an equivalent size slit width as if you were taking like a long slit or a cross dispersed, and you can get the same ITC capabilities as you would for the IFUs.
Great. And we have a response here from our participant who asked that question. Thanks, good to know. I've been using the online one anyway, and just wanted to make sure it wasn't an issue on my end. So perfect. Thank you.
That looks
Brian.
like an OT bug. Yeah.
Yeah. And I guess another question I saw says, can observers control, okay, sorry, it's direct to me, I guess. Can observers control themselves, the setup of their observes? I guess I didn't quite understand this question. Can observers control themselves, the setup of their observes? What? So observer, you mean the telescope operator and the observer at night? Yeah, I guess I just realized there's a specific question direct to me, and only direct
Oh, I
message
see.
to me. Yeah, I'm not quite following. If you could explain a little bit more in the text, that'd be great. Yeah.
But yeah, maybe so everybody has access to this OT. So y'all have access for your programs. Then all the contact scientists, NGOs have access. The Q coordinators have access, and the nighttime observers have access. And so anybody is able to modulate the setup here. And so if the observer finds at night, like let's say, we're working on a program and we accidentally didn't check the peak signal that was expected, and it was 80% full well depth. And then the observer takes the observations and conditions that are better than specified, and all of a sudden the detector is saturating. Well, they're gonna change things, and they're gonna change things around in a sensible way to still more or less get what you want. But so the detector doesn't saturate, or they'll give up and they'll throw it back to the contact scientist, and the next day then they can iterate. But in either case, you're not getting exactly what you want, right? Because you're not making that choice. And so this is why the phase 2 process is so important. You want to iterate and make sure that you have contingency upon contingency upon contingency built in, so that your preferred approach is implemented at nighttime. You want to take it you want to make things as easy as possible for Daniel, so that our observers don't have to think at night. And putting in notes is also really helpful. So like C would put, for this program, she would put like a blue note, and she would say, don't split, take these observations back to back. Any other like constraint, let's say she also was like okay with getting like IQ 85. She might put a note that says like program accepted under IQ 70, please try to observe under IQ 70, but can accept IQ 85. And so having all of these contingencies built in, baked in, we even do like for GMOS, there's 3 gratings that rotate out all the time. So we have the R400 and B480 in all the time, but there's 3 other gratings that are in occasionally. This is B1200, R831, and R150. And so if your program has, especially for targeted opportunity programs, if it has like an R150 component, sometimes the time of trigger or the time we're ready to observe your target, that grading isn't in. And so then you have to wait maybe several nights until that grading goes in. And the decision tree for that is every morning we decide, every weekday morning we decide what's the priority, which grading should go in. But I encourage like a lot of my PIs, check and see if you can use a different grading. Like if you have R150, can you use R400 and then just degrade the resolution a little bit? And we actually make multiple different observations, and then they would trigger whichever one was appropriate for that night given the grading. So they would have an R400 sequence, they would have an R150 sequence, and then they attempt to trigger the R150, and then oops, it's not in, so they already have everything ready for the R400. And doing that ahead of time is really, really important, so that you don't want to be making those decisions in a hectic moment when you just discovered something really important and everybody's trying to rush to take those observations.
Yes, exactly. Okay, so one last thing I do want to say. So I did try, look, you can add a like blue note, kind of scheduling note, right? Say don't split. And then in my case, since I want the monitoring, so several different ways to do it. If you really want a very specific monitoring, like very specific timing windows, you can add observing conditions here, right? You can set a specific timing window. You can a very specific timing window. But then sorry, I'm losing. Okay, it's just popping up all over the screen. Yeah, like this, right? You can say, okay, this is on this specific time. But in my case, it's not that rigid. I kind of just want one every 2 weeks. And then, but one thing I do want to do is if you click on this, you see this is an organization folder, right? So I actually want to put it into a scheduling group. In this case, they definitely would not separate these two observations, okay? So I'll put them into a scheduling group, and then I would rename it an epoch 1, right? And then I would just call this GMOS imaging. And then this ghost, right? I can just cut this and I paste it here and I call it ghost. Yeah. Because then you see in this case, right, they are actually grouped together. So this epoch 1, I have a GMOS South component, and then I also have a ghost science component. And then they will just be executed together when the QC schedule it. Yeah. Okay, I think that's all I want to show for this program. Still need a little bit more work to get it done. But you see, like if you click on epoch 1, right now the plan time is 1.5 hours. So it's about, look, like 20 minutes GMOS imaging, and then 1 hour, 8 minutes ghost. And then just when you do it, finally, you see like your allocated time need to agree to your plan time. So basically, I'm allocated 7 hours, 36 minutes. And then I just need to duplicate this epoch a few times. And then in the end, my plan time agree to this allocated time. And yeah, that'll be it. All right, with that, and I think I'm gonna stop here and hand it back to Brian.
Thanks, E. Just on that last point, one other thing that confuses me sometimes and confuses a lot of people that attempt to match up the allocated time with the PI charge time is that there's hidden overheads that are they're not always there. And so like one example, we have an observatory policy that basically every 2 hours, you got to assume we're going to move on to another observation. So we wouldn't normally, unless you have like a long transit or something, we wouldn't normally observe a program for more than 2 to 3 hours. So you assume one full reacquisition every 2 hours. So if C's observations were 3 hours for that observing block, in her case, it has to be scheduled altogether. So it's kind of debatable whether that would fall into this category. But if it was not required to be scheduled altogether, we would assume a full reacquisition, full acquisition for that observation. And so you'd have to add, in the case of like a GMOS imaging program, like 6 minutes to the overhead time. So that accounting is not done in the OT. This really gets complicated in the near IR, like GNIRS. You do acquisitions and then you do reacquisitions to account for flexure between our wavefront sensor and our instrument. So just if you have long observations, talk to your contact scientist to make sure that you're getting like the time accounting more or less correct. And we're good to like for most programs, if you get it within like plus or minus 10 minutes, it's fine. But if you start to go over more than that, then we have to like scale back on the total integration time or something like that.
Yeah, exactly. Yeah. Actually, I just realized I do have one more thing about ghosts. I feel like I should mention.
Okay.
So, sorry, just going back here, right? You see there's the red camera and the blue camera, right? And then there's the exposure count. So there's actually two ways to do it. I was just checking the menu to see what's the recommended way. Actually, this is not the recommended way to do it. Okay. So you can basically you can say, I want a 30 minutes integration and I want to do it twice, right? So one way to do it is just say read count times 2. There's actually another way to do it. Here there's observe count, right? And then the recommendation changes a bit. I just want to say, right now the recommended way to do it is actually to observe twice. So the reason is because this is one ghost setup, and then the data got stored, read out say one data file, and then you repeat this observation again, and then the same file got stored again. And it doesn't really make a change in your total execution time, but at the PI in this specific case, you actually get 2 data files. Well, kind of 2 data files, 2 separate exposures instead of 1 all bundled together. The bundle thing is, I guess, currently not the recommended way. So I just want to say, actually, right now the recommended way is to, if you want multiple exposures, use this observe times however many times you want to do it. Yeah. All right. I think that is it. Yeah.
Thanks, C. I think that's a good advertisement for how complicated the OT is and how like subtle a lot of these choices are, and how also we miss a lot of these things, right? And so it's not until we go back and like read the documentation and like seriously think about things that we can parse out these subtleties. We're also supporting a huge number of instruments, and so like I know my instrument fairly well, but Ghost I'm pretty clueless on, and so yeah. So anyways, reach out to us. You can see the OT is complicated. You can see like these decisions are complicated. So please do reach out to us if you have any ambiguities. And this can mean the difference between like good data and less good data. So because once we take the observations, that's when as long as the data are usable, that's when the window is closed. So make sure that you set up everything correctly, do your best beforehand. Daniel, can you guys hear us down there?
Yes, I think they can now.
Yeah, sure.
Oh, okay.
Muted.
Hey. Okay. How are things going? Are you guys gonna open today?
Well, we still have stable high dew points. Yes. I mean, if the dew points start to drop right now, we still have to wait half an hour to open and more half an hour to start to observe because of, well, tuning and so on. So yeah. We are still 1 hour from observing anything in the best case.
It's basically been constant. I mean, it's been fluctuating, but it's basically back to the same point that where we joined you. It looks like. Yeah.
I mean, just for people to know, do you want me to explain very shortly why we are close by the dew point?
Yeah, that'd be wonderful.
Yeah. So the dew point is, of course, is the point where the water starts to condensate on surface. So in Gemini South, we have a lot of cooling lines that goes in the instruments and a lot of computers. And if those cool lines have like a temperature, I mean, every time 6 degrees, yeah? So they are like copper tubes. So if you open right now, the humidity of outside will make this dew point the same as inside the dome, which now is, of course, not a threat because we are close with stable humidity and control humidity and so on. But if you open, we go to we have a dew point of 8 degrees, which is 2 degrees above the cooling lines. That means that water will start to condensate there, and we can see water dripping everywhere. I mean, inside the electronics. So this is a very serious thing that can happen. And that's why we wait for the dew point to get below 6 degrees. and be stable there, because as Brian pointed out, I mean, things oscillated, and then we have just wait a bit more to have sure that they're not going up again. So we are basically avoiding any electronic failure due to water dripping. Yeah.
What are some of the other conditions that you guys monitor to make sure the telescope and the instruments are safe?
Sorry, say again, Brian?
Which are some other metrics that you monitor to make sure that the telescope and instruments are safe? So, for example, I see that the wind speed is plotted here. This is something that you guys monitor. You want to give like people an idea of what else you look for as an observer and as an operator to make sure everything is safe and ready to take science?
Yeah, that's a good question. So this is the main role of the operator, which is, I mean, the responsible for safety in general. I mean, it's the head of safety, let's say, during the night. So if the observer has, I mean, there's a high priority target that must be observed, conditions are more or less good, but the operator decides for safety not to open, we have to respect and should respect the decision of the operator, right? And the decision of the server is to call the night. So the operator cannot decide to call the night earlier. And that is, I mean, this is kind of a division of big decisions for night. These are the most two important decisions that we take at night. If you close or open, or if you call the night or not. So for opening, we have basically the wind that cannot be above 20 meters per second. And humidity cannot be above 85%. Yeah. And the dew point, as I was explaining before. And one more, Piera, do you remember something more?
No.
Of course, clouds that are threatening some rain somehow, because sometimes the humidity is like very low, like 10%. But we have high clouds that can actually rain. So it's,
I mean, it snowed here. I think 2 weeks ago it snowed when it was like low 40s humidity. Just came out of nowhere.
Yep.
Yeah, these are special places on Earth.
Yeah, it's interesting because in Gemini North you have much more different kind of threats than we here in the South, because
Kilauea, for example, the volcano.
Yeah.
So our humidity limit changes when Kilauea off gases, and we also do like monitor the particulate counts with the other observatories here. I assume you guys don't have that.
No. We have some fire in the south here in Chile recently. I think it's still going on, and we can detect dust in the dust sensors already.
Yeah.
So, but I mean, it's not something that we are worrying about the telescope. But if it gets higher, the content of dust, it can make people have to wash the mirror again. So it's bad as well.
It was actually I was observing on Gemini North on Friday night, and Thursday night was like a snowstorm basically, and then it dried out like super fast, and so it was so dry and so windy Friday night after this like fairly humid event that it was like kicking out clumps of dust, and we were getting it on our monitor here, and it was to the point where we were thinking we might have to close at some point. Luckily, we didn't have to. But things change fast. But this is why Q observing is great, because your program's in there for the entire semester, so you get to average over all this insanity.
Yes. We expect we have some space for this. Yeah. For weather loss.
Great. Thanks, Daniel. Thanks, Piera. I think we're getting like pretty close to the end of this session. So is there any like last questions? Or of course, this is not the end. You can always reach out to us in any.
Yes, we have a question.
Tiago?
Hi.
Hey.
Nice to meet you all. First, thank you for this meeting. I'm actually, this semester is my first program, Gemini as a PI.
Congratulations.
and I'm learning a lot from this meeting. I had a lot of doubt using the OT naturally. My program is to use iGreens to observe some red giants in open clusters, and my question is about calibration stars. In previous Gemini programs, my advisor they he said that the calibration stars were selected by the Gemini staff team, but this semester my contact scientist he told me that I have to select these calibration stars, and I was wondering if this is a work for the PI or for the Gemini staff.
Usually a team effort. So we generally like it if you do a search yourself, because we don't necessarily know exactly what parameters you need for like a telluric. I mean, some people say, oh, I absolutely need a like A0B star. Some people are okay with B stars. So yeah, so you can use our telluric star search tool. It's not comprehensive. So, if you really want to find something comprehensive, use Simbad. I know that there's holes in our telluric search, but it's pretty good for a first catch. And so you can put the spectral type that you want, subclasses as you like. You put RA deck of your target, delta degrees off of the target, and then you can get a pretty good idea. And then you can input those telluric stars into the OT, and then you can use the plotting tool there to show the air mass curves. And typically what you want is an RA, if they're at the same deck, RA that's offset by about half of the time of your observation. So if you have a 2-hour observation, do about an hour offset in RA. And then, of course, if the deck changes, then in order to air mass match, then you have to modulate the RA a bit. But that's generally what's done. And you'll find it's not a like standard approach. Like every contact scientist is different. But we generally prefer if the PI at least takes a look and makes a guess at what they want, and then we can kind of leverage off of that, because we don't really want to suggest a star and then you can't use it for your science or something like that. So I don't know, C, do you have anything to add?
Right. I actually want to say, Brian, what you said is for the infrared observations. For Ghost, since it's optical, so I just posted a web page there. So maybe you can take a look, Tiago. So the baseline calibration is what the observatory provide, right? So we provide bias, flat, wavelengths, and actually that's it. We don't really provide any additional calibration. So any kind of flux standard, radial velocity standard, they are count as program calibration. So these are actually come out of your science time. So yes, you do need to define your own thing, but it actually come out of your science observation. For example, my ghost program, I actually don't care about that. So I'm not taking any flux standard or any of the other standard. But for your program, if you need, like the program calibration is there, if you need a telluric standard, if you need the spectrophotometric standard, you do need to provide them it's yourself and then defined in your program. And then it's actually being treated just like your science observation. Yeah.
Sorry, Tiago, did I understand correctly that you were using iGreens too, or did I misunderstand?
Yes, it was iGreens too.
Oh,
okay.
I was confused. Sorry, I thought it's
Okay.
Ghost.
Sorry, I didn't know if I messed that up.
Okay, yeah. Then Brian's right. Yeah.
No, but I mean it's a good point. Also, like every instrument's different, and like optical, we would take baseline calibrations, but we wouldn't necessarily take like for imaging observations, we actually do take a photometric standard every night, but for spectroscopic observations, we don't. So it is wavelength dependent and mode dependent, instrument dependent. But yeah, the advice I gave for the infrared will work. So yeah, and feel free to suggest a set of stars, and then your contact scientist, I'm guessing I know who it is, he'll suggest back, he'll double check those, make sure everything's good.
Okay, thank you. I've selected calibration stars, but I was not sure if they are really adequate. I checked the plot during the night, and it all seems fit, but I wasn't 100% sure. But you need to double check, right? So
yeah, it's like sometimes, especially for like L&M band observations with G-nears, so longer wavelengths than Igrans 2 can look at. The tellurics, it's really hard to build up the signal to noise in the tellurics, and usually the observations are limited by the signal noise of the tellurics. But in most cases, short word of L, so K, H and K, like where Igrans 2 observes, you build up signal noise really quick on the tellurics. So you probably should check in with your team or do the calculation of what you actually need for the signal to noise for the tellurics. But I'm guessing that's not going to be the limiting factor for you. So any bright object is probably going to be okay. And you also want to think like, does your program specifically need tellurics? Some programs don't need tellurics.
I don't think so.
That's something to discuss, because a lot of Igrans 2 programs, I don't support Igrans 2 that often, so I'm not familiar so much with the decisions, but a lot of programs don't need the tellurics. If you're measuring like radial velocities or something like that, then you don't really need the tellurics. So that's just something you double check with the contact scientists and ask, is this really necessary? You can just even like quickly explain the science or ask them to look at the science, and they'll give good advice.
Okay, thank you.
Any other last questions by anybody? Oh,
Yes. So
Hi.
first I see Jerry. Yes, Jerry, go ahead.
Hi, this is Jerry from Canada Western University. I have a question about the charge time. So in the phase one, we submit the time. For example, I'm using the iGreens. So I submit the science time and another like 3 hours of calibration time. But in the phase two, like in the OT, the time only assigned to me was the science time. So I only configure all the science target of my program and fill up with this hour. But the rest, like 3.5 hour, it's just it's not clear listed in OT. I wonder whether and the selection of the telluric is just depending on me. I wonder how the observatory is going to charge this time, and is this going to charge like very precisely or what? The science kind of this partner calibration time was a little bit vague to me.
see, did you want to take that one?
Yes, I'll do my best. Yes, it is confusing. So
It is super confusing, yeah.
I know. So let me make sure I understand your question. So your question is asking how much do you worry about partner calibration time? Is that kind of what it is?
Yeah, I basically don't understand this part. I submit like 20 hours for iGreens that include all the scientific requirement and calibration requirement. And suddenly in the OT, I figure out that just to take like 3 or 4 hours was taken out from my time, and I cannot really configure that 3 or 4 hours. On the other hand, if you give me like the total time of 20 hours, I can configure maybe a little bit less of the telluric, maybe a little bit more exposure or vice versa. But right now, it's just 3 hours was taken out from my program, and I cannot really do about that. And support astronomer told me, scientists told me that I don't really need to worry about that time and just need to configure the exposure of the telluric, and the observatory is going to take automatically, well, depending on what telluric star I'm selecting. And they are going to do like one telluric per 1.5 hours, something like that. So I don't really, this kind of time is not precise for me. So what's the matter need with that to configure that time so precisely in phase one, and we got taken out, I feel. Yeah.
So Yeah, I think I understand. So yes, first I acknowledge it is confusing. So hopefully it will be solved with GPP. So I think the thing is when you submit phase one, right?
Yeah.
So if you remember, like I haven't used for iGrants 2 specific, but I'm pretty sure in iGrants 2 you need to put a science time, and then it will
Yeah.
add some additional, tell you that's a total time, right?
Yeah, that's something like a proportional. So like
Exactly.
every 2 hour per half an hour, something like that.
Exactly. So that additional time is actually your baseline, like additional calibration time. So
Okay.
that's why. So actually, in the phase one, it did automatically add in. So then your total time, your total request in phase one had already included this additional like partner calibration time. Um,
Okay.
so that's why like what it really matters is your total phase one requested time. And then in phase two, when you give you the time, it will be the total time. And then your program time maybe say 20 hours. The additional 5 hours is hidden, but it is embedded in your time request. And how it was calculated,
Okay.
it just not on average, like just as I said,
Okay.
proportional to your time.
Okay.
So basically in phase one, you just want to make sure your total time request is correct. Yeah.
Okay.
But
Okay.
in phase two, you can really not manually, I mean, you don't have the superpower. Your contact sensors can, but they
Yeah,
will.
exactly. My time got taken away. So, but for example, if my program now this program I need like a super long telluric correction, like I need a 3 hour telluric just exaggerating, okay, 3 hour correction for only 2 hour scientific exposure. That's should it just overshoot the 2.5 hour that I put in the phase one. And in phase two, in the OT, they are going to count the 2 hour scientific exposure. And but I put 3 hour. They are going. Are they going to complain or something like that?
Right, I see your point, but typically
Yeah.
telluric is very short, right? So I think we
Yeah.
typically budget maybe 15 minutes for the telluric, and then, but you are right, like in practice, there's nothing preventing you from putting a 3 hour telluric time. It wouldn't count.
Sometimes the iGreens need the telluric was like 10 magnitude, and the iGreens need to go to like 20 minutes or even half an hour, something like that. And sometimes it's not that short.
I see.
So that amount of time is not really, that's not charged to you as a PI. So that's
Okay.
all encased in this partner time. So if
Okay,
that's the
I just
telluric
don't care about that part in phase one, and don't
as long
care
as you
that
have
so
all
much.
so as long as your science targets have the integration time that they need scientifically, the rest is kind of immaterial. That all gets thrown into a big partner pool that if you have a telluric that's super faint and that's the only one that's going to work, we're going to try to find you a better one. If that's the
Okay,
only one that
yeah,
works,
yeah, sure.
then you
That's
don't have to worry about
understandable.
it.
Mm-hmm.
Yeah,
Okay,
that's all
thank
thrown into
you.
partner time. Yep.
Thank you very much.
So just to say that time isn't taken away, it's just dedicated to this like kind of nebulous calibration time, and it's a very approximate thing. It's by need, and it can be more or less time. In a program of your size, that's 20 hours. I mean, I would imagine the time accounting is going to be for the partner time, like plus or minus an hour at least.
Yeah, like 3 hours something. Yeah.
So that's in the noise.
Okay, thank you.
Yeah. Thanks, C, for explaining that. It's one of the most complicated concepts at the observatory, and it's one of the most boring too.
No problem. Doing my best. Yeah.
Okay, I think we should respect everybody's time and call it. But thank you all for joining us. And I'll send out an email with the videos of some of the instrument scientists talking about phase two stuff. We'll send out a video of this session. And thank you so much to C and to Daniel and Piera and the students in La Serena for joining us. And I hope your guys' dew point drops down and you get to open sometime tonight.
Yeah, in the second part of the night for sure. Then I call you back.
Cool. Okay. Thanks, everybody. Aloha.
Thank you, Brian. Thank you, Jamika. Yeah. Bye.
Thank you, everyone.
Thank you, everyone. Yay.